Imagine a group of girls sitting in a circle with apples. The teacher enforces a strange rule. If any student has way too many apples compared to her neighbors, then the teacher steps in, takes out one apple from her and gives one apple each to her neighbors. Could this process go on forever? Could there be an infinite number of cycle transfers? Or does this chaos eventually settle into order? We're going to solve this problem today using an important technique that often comes in Olympiads. Let's look at an example. Supposing you have a bunch of girls. Now look at the top left girl. Okay, she has 4 apples, but her neighbors combined have only 3 apples. The teacher steps in and she redistributes the apple. And now that girl has 3 apples, 1 apple less, and her neighbors have 1 apple extra. Now if you look at this problem, as the teacher keeps redistributing the apples over and over again, it could go on forever, right? Because the number of apples seem to be increasing. The teacher always gives 1 extra apple because she takes away 1 but she gives back 2, right? So is there any reason for it to go down? If you look closely, there is an answer. It might just be because the number of apples are actually distributing in such a way that the numbers are becoming closer to equal. 1, 4, 2 is very far away, 4 is very far away from 1 and 2, but after redistribution, 2, 3, 3 are pretty close. But how does one write a proof that she cannot go infinite steps? Okay. To understand this, we are going to focus on one important idea in mathematics. Okay. So for this problem, you could imagine the teacher's mu is a round, and the number of apples with each girl, that is the distribution of apples, is a state. So we are going to introduce a very important notion, what's called a monovariant. Okay. Now what is a monovariant? It is something that is varying monotonically. Basically, you have to associate a number to a state in such a way that the number is always bounded below, let's say it's non-negative, and the number decreases every round. Okay, what is the point of constructing such a number? Notice, if you have such a number, the teacher cannot make infinitely many moves. Because if the teacher did make infinitely many moves, then the number m will reduce every round and eventually the number will cross 0. That contradicts that m of s is always greater than or equal to 0. So this contradiction proves that the teacher cannot make infinitely many moves. So to prove that the process will stop, we just have to construct this number. So how do we solve this problem? Let's go back to that example. Okay. Now in this example, if you fill in a bit of story and if we think of these girls as having apple envy, we'll be able to solve this problem. Imagine every girl in the circle wants to have the maximum number of apples. They're all envious of that girl who has 6 apples. And the amount of apple missing to become the max apple person is the number apple envy that we assign to each person. In this case, 6 is the maximum number of apples, and the apple envy, the total apple envy, is 24. In other words, if the teacher had 24 apples, if the teacher could just distribute 24 apples, then everyone could get 6 apples basically. Okay, so that's what is apple envy. And I claim apple envy is basically the monovariant we are looking for. Okay, so let's in fact prove that. So let's set up the mathematical notations. Imagine you have a state with the n number of people in a circle, and let's propose the following notation. Capital AK is the maximum number of apples in any round. Okay, let's say you are in state SK. Okay, at the end of round K, you are in state SK. In that round, let AK be the maximum, capital AK be the maximum number of apples, and capital M of SK is the total apple envy. Very clearly, apple envy is non-negative, but also note that M of SK can be written as n times AK minus the total number of apples. Capital NK is the total number of apples. Okay, the only thing now remaining is to show that this number reduces every round. We already shown it's non-negative. If we show it reduces every round, we are done. Let's go back and check what happens to the total number of apples. Remember that the teacher takes 1 apple away but gives out 2 apples. So the total number of apples increase by 1 every round. Alright, so we are going to show that the total apple envy reduces every round. Okay, it strictly reduces. To do this, we are going to break the problem into 2 cases. One in which the maximum number of apples does not change, it remains the same, and in other case the maximum number of apples changes. Okay, so the first case is when the maximum number of apples don't change. In this case, if you write down the formula, you will see it's n ak plus 1 minus nk plus 1. Well, the total number of apples changes, it in fact increases by 1 from the previous round. The maximum number didn't change. So if you calculate it, you see that the total apple envy has gone down by 1. Yay, we have solved in this particular case. What remains is the only other case where max apples actually change. Well, now let's think about it. If the maximum number of apples changed, there's only one way that can happen. It can happen because the teacher chose the person with maximum number of apples and removed one apple from them. That means the maximum number of apples can only go down by 1. So let's put that into the calculation. AK plus 1 should equal AK minus 1. And the total number of apples anyway increases by 1. So if you do the algebra, you see it's MK minus N minus 1. Definitely MK plus 1 has reduced. So we proved that in both cases, MK plus 1 has reduced. In other words, this number M is indeed a monovariant, and we are done. Therefore, the teacher should stop infinite number of moves, and that's the end of the problem. If you want more videos like this, please comment below, share this video if you liked it, and follow me. See you until the next aha moment.